Okay, yep. So my name is Tiago Costa. I'm a PhD student at the University of Cambridge, and this will be a sort of overview of results of a recent series of numerical simulations using the code IREPO. And the purpose of these simulations was to examine the role that energy and momentum, the position by AGN on the interstellar medium, have in driving large-scale outflows, the clear baryons from the central regions of galaxies that would otherwise form stars or accrete onto black holes. Now, just to give you some numbers coming from observations, the last few years have provided us lots of observational evidence for outflows driven by AGN, and these are typically signaled by observing emission lights with very broad wings. And in this case, I'm showing you observations of the CO line, and the CO line traces molecular gas. And what you see is that apart from this narrow component, you have these extremely broad wings that trace molecular gas flowing out of the quasar at speeds up to 1,000 kilometers per second. And then you can estimate different properties of the outflows. These are quite uncertain, but different authors seem to agree on at least on these properties. So the typical masses flowing out tend to be 10 to the 8 to 10 to the 10 solar masses. Interestingly, the momentum flux of the outflows is several times the momentum flux in the radiation field of the AGN. So this is what you call a momentum boost. And typical values tend to be about 20. And the kinetic luminosity of these outflows tend to be a few percent of the bolometric luminosity of the AGN. So typically 1 to 5%. And these outflows have long been invoked in order to explain the M-sigma relation. So already in 1998, there's a paper by Joe Silk and Maarten Rees. And afterwards, Andy Fabian, Andrew King, and several other people explore this further. And the basic picture is if you balance the force or the energy of an outflow with the weight of gas in the galaxy, you can actually reproduce a relation between the black hole mass and the velocity dispersion of the bulge of the galaxy. And the predicted scalings are in the range of 4 to 5. So the latest sort of observed one tends to be somewhere in between. And the normalizations vary quite widely. So certain types of outflows, the so-called energy-driven ones, tend to give far too low normalizations. But if you have a momentum-driven outflow, the normalization is in fact extremely close to the observed one. So analytical models with very simple assumptions manage sometimes to get both the scaling and the normalization correct. From the numerical point of view, feedback from AGN is being modeled by letting a fraction of the bolometric luminosity of the edge couple either via momentum or thermal energy to the gas. And in this video, you see two colors. So blue shows inflowing gas, red shows outflowing gas, and the brightness shows radial velocity. And what you see is that when you have gas flowing in, almost radially inward, so this is for a 10 to the 9 solar mass black hole at redshift 6, you make the accretion rate go up dramatically, and you drive these bipolar outflows, which are very hot, propagate along the voids. On the other extreme, in the analytical models, you have to make very simple assumptions. So typically, you have a static potential in a spherical halo. You have the gas is at hydrostatic equilibrium in this halo, and then you drive an outflow from exactly the center. And there's two main pictures in how you can do this. One of them, which we'll not be talking about, is by radiation pressure, and this was sort of pioneered by Andy Fabian in a paper in '98. So here you imagine that the gas in the galaxy is dusty, and the dusty gas absorbs the photons very efficiently, and you drive an outflow. In the other picture, which I'll be talking more about, which was sort of developed a lot by Andrew King, is in which the coupling between the energy and the momentum of the AGN is hydrodynamical. In this case, you need to invoke a very fast inner outflow. So this tends to be almost relativistic, about 10% of the speed of light. And because it's extremely supersonic, what happens is that you form this so-called reverse shock. And then how you then drive an outflow depends on what happens to the So in this case, sorry?
None of those cases actually are used.
Yes, so I'm here talking about mostly the quasar mode, in which it is thought that most of the gas is expelled by a very broad outflow rather than a jet, which would operate in the other radio mode. So I'm focusing on this picture now. So the gas that passes this reverse shock is extremely hot, 10 to the 10 Kelvin, you can estimate that. And then what happens depends on the fate of this energy. If this energy is preserved entirely, this region, which I called region B, this is the gas, the wind that has been shocked, expands adiabatically, and you get an energy-driven outflow. The resulting scaling is proportional to sigma to the power of 5, perhaps a bit too steep compared to the observations. If you instead radiate away all the energy that you've created in this shock, and this you actually need inverse Compton cooling, you get the opposite. Now the only force that is exerting on the interstellar medium is the ram pressure of the inner outflow. And this you called a momentum-driven outflow. So what we've done here is to take a step back. So the motivation is twofold. We want, on the one hand, to have subgrid models in cosmological simulations that are well calibrated by analytical models. So we wanted the models to do what they should do in circumstances in which you should expect them to match analytical solutions. And on the other hand, we want to investigate whether you can still drive an M-sigma relation, which works perfectly well with these simple analytical models. We want to check whether that still holds in cosmological simulations. For this purpose, we've run simulations with our repo. Like in analytical models, we've taken a static potential, a Hernquist potential in this case, with these parameters, 10 to the 12 solar masses, and a gas fraction of 17%. We also assume the gas to be at hydrostatic equilibrium. We do not actually include black hole accretion. We don't want to add more subgrid models. We really just want to focus on what happens when you couple energy and momentum. So instead, we run several simulations with different black holes, and we leave the black hole mass fixed, and we explore different values in this range. And this range encompasses includes the value at which you actually get an unbound shell, as I'll show later. We assume the AGN to be constantly emitting at the Eddington limit. So this is unrealistic, but it's what analytical models assume quite often. So in order to mimic these, we make this assumption as well. And just to show now, to jump to the results, in both energy and momentum-driven outflow cases, like analytical models, we drive this shell. So this has been discussed also when people were discussing stellar winds back in the 70s. And in the energy-driven case, you actually get these instabilities that form because you have this bubble of very hot gas in the center, which is expanding adiabatically. So these are Rayleigh-Taylor instabilities. And in the momentum-driven model, you can see that at matching times, it propagates less quickly. So this already gives us a hint that the momentum-driven outflows are less efficient. We have compared these models explicitly with analytical solutions. So the solid lines show, so this is time against the radius of the shell. The solid lines tell you the analytical solutions to the same halo, and the dots give outputs of our simulations at the same time. So what you see is that in the entirety of the simulations, you predict these, the match between the analytical and numerical simulations is extremely good. What happens at late times is because of the development of these instabilities, it stops actually making sense to make this comparison because we no longer have a thin shell, which is always assumed in the analytical models. But in the energy-driven outflow, we have mimicked this quite accurately. In the momentum-driven outflow, what you see is for high black hole masses, so this is the case for 5 times 10 to the 8 solar masses, the agreement is very good. And interestingly, what happens at lower black hole masses is that it behaves, it diverges from the analytical solution. In the case in which the black hole mass is too low to drive an unbound shell, the numerical simulation qualitatively does the same thing, but quantitatively not exactly. And the reason is that you actually enter the regime in which the propagation of the shell is subsonic. And analytical models always make the assumption that you have a strong shock. When the speed of propagation of the shell is comparable to the speed of sound in a halo, you actually need to take into account the confining pressure of the halo gas. And this is what, if you check the time at which the deviation occurs, matches the time at which the solution enters the subsonic regime. But in any case, the conclusion holds that if you have a momentum-driven outflow, there is a critical mass, which is this one, matches normalization and the scaling very well with the observations. And at this critical mass, the outflow is unbound. You can clear the baryons away from the halo and quench the star formation and black hole accretion. So we now want to check this in cosmological simulations. So these are simulations in which you actually form black holes. In this case, a 10 to the 9 solar mass black hole by redshift 6. And we have included exactly the same models. So we have the energy-driven model, the momentum-driven model. We still do not have a black hole accretion. Again, we just keep the black hole mass fixed. And what you see in white are velocity contours of the resulting outflow in the cosmological simulations. And in yellow, the dashed line, what you see is the corresponding halo. But if you spherically averaged it, so exactly the same halo, but spherically averaged, and the same feedback model. And you can already notice that the geometry is completely different. The outflows escape along the voids. They escape very inefficiently along the inflows. The velocity structure is completely different from these isolated models. But overall, energy-driven model at the black hole mass that would place this halo in the M-sigma relation drives a large-scale outflow. The most interesting finding is when you include the momentum-driven outflow in the cosmological simulations, we do not really drive any appreciable outflow. You can see that the inner regions, which would otherwise be completely emptied if this halo was isolated, are still filled with gas. And this gas is still flowing in along these filaments and feeding the central galaxy. So whereas in isolation, a momentum-driven model gives you a normalization and a scaling in very good agreement with the observations, these cosmological simulations tell us that because you need to account for the extra momentum carried by these inflows, you need something much more efficient than momentum-driven outflow. And suddenly, the normalization and the scaling is more difficult to understand. Now, just to show these last plots, this shows just the momentum flux and the kinetic luminosity of the energy-driven outflows. As a function of radius, you can see that we have these momentum boosts. So this is the integrated values, so several times L over C, like the observed ones. This is what you need to actually revert to the inflows and prevent the central regions from being replenished, and typical kinetic luminosities of a few % of the bolometric luminosity, like required. So I'll now just leave you with the conclusion slide. Thank you.
Start seeing these instabilities develop, does that eventually, at some point actually stall the flow? I mean, at some point, does it become so unstable that you really mass actually isn't escaping?
Yeah, so in a more realistic case in which you don't actually have Eddington luminosity throughout, you would coast. And I think you would, what probably happened is the regions that lag behind would probably still fall towards the black hole. And this is what other people observe as well. But in this case, we constantly injecting energy. So at least in the time scale I've run this, you actually don't get any gas in the center. But with time, you would get more and more disrupted, and the instability should grow.
So I guess my broader question is, do you actually have to resolve those instabilities in a simulation to get the answer right?
Right.
Does that mean the cosmological simulations are problematic?
So in the cosmological simulations, obviously, we don't even, in this, we had a resolution, well, the minimum cell size is about 60 or 70 parsec. So I think we cannot even resolve how the gas feeds the black hole. And obviously, we cannot resolve the instabilities in great detail either. But obviously, yeah, you would want to resolve them if you want to get the picture correct.
Let me just ask before we take some questions. The next speaker, Mark, to come up. Okay. Questions? Yeah.
As it compares to the two model energy momentum, two slides back, gas distributions on crystal particles, which one gives a better match to observations?
Sorry, which one?
Which one of these models gives a better match to observations of distributed gas on those scales?
You mean in terms of the outflow or of the M-sigma relation?
No, in terms of the gas.
In terms of the gas distribution? Well, there's, I think, there are very few observations, at least at this redshift, of these outflows. But there is a quasar redshift 6.4, which has a very powerful outflow, which would not be described by the momentum-driven one, because he would really not doing much to the gas. So the one which would be a much better match to the observations would be the energy-driven one, in which you actually get speeds, outflow rates, and kinetic luminosities comparable with the observed ones.
building up more momentum such that you could reproduce that result if you used a already gone through some phase where it built up 20 L over C.
Yeah. So with momentum, I think the only way you can actually get a boost is if it's radiation pressure. And then you'd require very high optical depths of at least 10. And I think this is work done in the past has always invoked these very high optical depths. Well, you can show from the hydrodynamical models that in the momentum-driven outflow, the momentum flux can never exceed L over C. And this is in the hydrodynamical case. And this is the reason in this case why it fails. It's because if you were static, you would empty it. But now we need to take into account these very thin filaments, which carry a lot of momentum, and suddenly you need 20 L over C or something to actually revert them.
I mean, I was sort of thinking that maybe you had some early energy conserving phase where a 30,000 kilometer a second wind shocks and you've got a bubble, but maybe that bubble is all inside central 10 parsecs or something.
The problem is that the bubble is about 10 to the 9, 10 to the 10 Kelvin. So to cool it and to transition to the momentum-driven regime, the best hope is to have inverse Compton cooling, and you need to be very close to the AGN for that to be efficient. At already kiloparsec scales, it's very difficult to see how you cool this bubble. Even free emission, you can show that the cooling times are enormous.
So it's common to grab here. Why don't you go next? Do you want to take one more question while you're setting up? Any more questions?
Really stupid question. What's M sub sigma there on that slide?
What's the M sigma?
M sub sigma.
Yeah, so this is the mass of the black hole that would place the halo in the black hole in the M sigma relation. So it's the corresponding, yeah. Okay, yep. So my name is Tiago Costa. I'm a PhD student at the University of Cambridge, and this will be a sort of overview of results of a recent series of numerical simulations using the code IREPO. And the purpose of these simulations was to examine the role that energy and momentum, the position by AGN on the. I'm showing you observations of the CO line, and the CO line traces molecular gas. And what you see is that apart from this narrow component, you have these extremely broad wings that trace molecular gas flowing out of the quasar at speeds up to 1,000 kilometers per second. And then you can estimate different properties of the outflows. These are quite uncertain, but different authors seem to agree on at least on these properties. So the typical masses flowing out tend to be interstellar medium have, in driving large-scale outflows, the clear baryons from the central regions of galaxies that would otherwise form stars or accrete onto black holes. Now, just to give you some numbers coming from observations, the last few years have provided us lots of observational evidence for outflows driven by AGN, and these are typically signaled by observing emission lights with very broad wings, and in this case, 10 to the 8 to 10 to the 10 solar masses. Interestingly, the momentum flux of the outflows is several times the momentum flux in the radiation field of the AGN. So this is what you call a momentum boost. And typical values tend to be about 20. And the kinetic luminosity of these outflows tend to be a few percent of the bolometric luminosity of the AGN. So typically 1 to 5%. And these outflows have long been invoked in order to explain the M-sigma relation. So already in 1998, there's a paper by Joe Silk and Maarten Rees. And afterwards, Andy Fabian, Andrew King, and several other people explore this further. And the basic picture is if you balance the force or the energy of an outflow with the weight of gas in the galaxy, you can actually reproduce a relation between the black hole mass and the velocity dispersion of the bulge of the galaxy.